Population parameters are unknown parameters. If they are unknown, but we would like to know about them, what to do? So can you give me an example of a population parameter? Hello? Anybody? Mean, population mean, mu, and
standard deviation.
Standard deviation, population standard deviation or population variance, sigma squared. These are examples of population parameters. Now the thing is, any variable, a random variable, it has a mean, it has a variance. We are talking about population, mean, population variance. You know, population mean means expected value. Population variance is expected value of x minus mean whole squared. So that's another expected value. So these are the population mean, population variance, population parameters. These are unknown. Then here is this sampling distribution. We focus on sampling distribution of sampling mean, sample mean or sampling mean. So when you have a random variable y with mean mu and variance sigma square, then what you do as a statistician, you take a sample, you draw a sample, a random, hopefully a random, thoroughly random sample. Then mean of that sample is called sampling mean. Now that sampling mean is a random variable. If y is a random variable, then sampling mean, which you are taking randomly sample, that mean of that sample is also a random variable. We told you in the last class how sampling mean is becoming a random variable. How is that? Do you recall? Hello? How is sampling mean a random variable? Hello? Nobody wants to say anything? Okay, it's a random variable because you can draw many samples. Let's say you are taking a sample of size 30. Size 30 means you have 30 observations in the sample. So let's say you are trying to see the salary of the college teachers in the city. Okay, salary. So obviously the salary varies from college to college, university to university. You take a sample, you talk to 30 teachers, collected their salaries, and then you got the mean. So you got the sample mean of salaries. Now that's one mean only. If another researcher also goes and collect another sample from the same population, teachers, college teachers of the city, and get their salaries. 30. She also talked to 30 teachers and 30 salaries, added them, divided by 30, get a sample mean. So how many sample means can there be? Hello? Hello? How many samples can be drawn with replacement? Are you guys with me?
Yes, Professor.
How many samples can be drawn?
Professor, I lost my connection. Can you please
You
repeat the
lost
question?
it, but some other people, I'm asking other people who did not lose the connection. How many samples can be drawn? Hello?
Professor, is it like according to the like information like name, age, salary like this?
Yeah. So how many samples can be drawn?
30.
No, 30 is the observation. You guys have to be clear. You did probability statistics. 30 is the number of observations in one sample. So you draw a sample. How many teachers you have talked to? 30. You have collected salaries of 30 teachers. So how many observations do you have in your sample?
30.
30 observations. You have drawn one sample, and in that one sample, you have 30 observations. So your sample size is 30, okay? Meaning you have one sample with 30 observations. Now, I'm asking how many samples like that with 30 observations, how many samples can be drawn?
We can draw as many as we want.
As many as you want. That is the thing. With replacement, you can draw as many samples as you want. Now, so how many sampling means will you get?
If we, for example, if we take 15 samples, then we get 15 sampling means.
15 sampling mean. If you theoretically speaking, you can draw 1,000,000 samples. You can get 1,000,000 sampling means. Theoretically speaking. So then sampling mean has become a variable. Okay. Sampling mean has become a variable with millions of values. And and with probability assigned, because one mean can occur 50 times, another mean can occur 40 times, 42 times, and so on. So sampling mean itself has become a random variable. These are theoretical issues in the sampling distributions. So, but for us, this is just enough to see that if y is a random variable, then sampling mean y bar. Y bar equals summation y divided by n. Y bar is also a random variable, because millions of samples can be drawn, and then you can have millions of sampling means. Then that sampling mean has a distribution. Sampling mean is becoming a random variable. Okay, that is interesting. But more interesting is if sampling mean y bar. What is y bar? Summation y over n. Okay, sampling mean is not expected value of y. Sampling mean is y bar. Population mean is expected value of y. And we know how to find expected value of y. Now this is y bar, sampling mean, which is summation of y over n. N means sample size, number of observations. That sample mean y bar, theoretically you can draw millions of samples, but in practice you will go and draw only one sample of size, say 30. Now this sampling mean y bar is a random variable. It has a mean and it also has a variance. Y bar, which is sample mean, that sample mean has a population variance. Obviously, if it's a random variable, it has a distribution, then that distribution has a mean. What will be the mean of y bar? That is very interesting. That's really, really interesting. That's where all strength lies. So I'm asking, what is if y bar is a random variable, if y is random variable, then sampling mean y bar is also a random variable. Now, if it's a random variable, it has a distribution. Then expected value of y. And then the question is, what is the expected value of y bar? So the first question is, if y bar is a random variable, then what is the expected value of y bar? So once again, this sampling distribution is the strength, is the basically everything is based upon this sampling distribution, theoretical sampling distribution. What it's saying is saying if y is a random variable, then y bar, which is sample mean, is also a random variable. If y has a mean mu, then the question is, what is the mean of y bar? Any?
Will it be same as the population mean?
Yeah, like summation, then y into probability of y.
Yes.
Is that how it is?
Why probability of y?
Because it's y bar, that's why.
It's y bar. It's not y. It's a different random variable. It's random.
Professor,
It's not a constant. When you say probability of y, you are saying y bar probability of y bar equals probability of y. No.
Professor, will the sample mean, the expected value of sample mean be the population mean?
Exactly. You can prove it. Sampling distribution of sample mean. It can be proved that if expected value of y is mu, then expected value of y bar will also be mu. That is the strength. So why is that the strength? If so, then you can use y bar as a representative of mu. And in this literature, it's called unbiased estimator of. We will explain what unbiased means and all this later on. Unbiased implies y bar is an unbiased estimator of what? Of what?
Of mu.
So roughly speaking, for now, it's later on we will give specific definition of unbiased estimator. So it's saying y bar is kind of okay. Y bar is kind of okay to talk about mu. Why? Because mu is not known. What do? We want to know mu, but there is no way we know mu. So we get a y bar, which is basically a sampling mean. We took a sample of 30 and then we added them, divided by 30, we got sample mean, and we are talking about mu. How is that possible? That's possible because y bar is an unbiased estimator of mu. That simply means expected value of y bar equals mu. The y bar is a distribution. That distribution has a mean. That mean and the population mean, y, mean of y, they are exactly same. Even though we don't know what mu is, I mean the value of mu. Is mu 55? Is mu 39? We don't know. But we know that if mu is 35, expected value y bar will be also 35. If mu is 55, then we also know that expected value of y bar also will be 55, so on. Yeah, question?
Professor?
Yes.
So like unbiased estimator of mu, does it mean because like from the sample is extracted from the population itself? So for that
Obviously, sample is extracted from the population, from this population, the distribution of y. There are millions of values of y's. Okay, we collected randomly only 30 from there, and then we found this so-called y bar. Now we are talking about mu. We are saying, oh, mean is something like 35, so on, or 34, or 30. How can we say that? You are making a big mistake. Yeah, true, there is a mistake, but there is also strength. Even though y bar is not equal to mu, but if you look at the distribution of y bar, the mean of that y bar actually is equal to mu. It can be proved. I can prove it right away in 2 lines, but I'll let you do that. Yeah, question? Yeah, go ahead. But let's say, so this is a fact. But if, let's say if it was not equal to mu, if expected value of y bar is not equal to mu, then it would have been a bigger mistake. It would have been a very big mistake to talk about mu just showing y bar. That if expected value of y bar was not equal to mu, then y bar would have been called a biased estimator. A biased estimator is no good for statistical inference. You need an unbiased estimator. We will see in a regression context, we need unbiased estimator of population parameters. Question, please. Hello. Do you have any questions? Do you see what I'm trying to say here? I mean, proving is in the book, you can prove, but do you see what they are trying to tell you? Why statistical sampling distribution theories are important? They are important because they are theoretically telling you that even though y bar may not be equal to mu, so when you are using y bar to kind of talk about mu, you are making a mistake. However, there is some strength in that. Why? Because even though an individual y bar may not be equal to mu, but on an average, y bar equals mu. Expected value of y bar equals that population parameter which nobody knows. Interesting. Have you done this kind of thing in the probability statistics? Estimation?
No.
Hello, be honest.
No, Professor. We have just directly done math.
You?
Professor.
We have directly done the math.
Yeah.
In the math.
We didn't have these explanations, Professor.
I don't get you guys. Did you do this or not?
Professor, like we did not have detailed explanation, but we did find out expectation means and stuff.
Yeah, but yeah, obviously maybe you did a rigorous mathematics behind this. But for us, you know, really, what is important is the intuition behind it, because we'll be doing that a lot. Basically, I would say the most effective thing statistics is doing is this: using sample to talk about the population. How can they do it? Because of the strength of the sampling distribution. Now, if I ask what is the variance of this y bar? Any guess? Huh?
It should be same as the population, right?
Huh?
Hello, Professor. How are you?
I'm good. Who is speaking?
Professor, this is Kajuli Akhtar. I just joined because of in my place don't
Okay.
have internet. That's why.
Where are you staying, Kajali?
In my village,
Where is that village?
it's Chakpur district.
Chatpur district. Oh man, you should send us some pizza, or else I will not give you attendance.
Yeah, I will send you email. Yes.
Yeah, just joking. Yeah,
Yeah, I understand, Professor. Thank you. I will send you email.
you email to TA and also copy. So variance of y. What should be the variance of y?
Professor, will it be the population variance by the sample size
The population variance
divided by the sample size?
divided by exactly.
Sam-
Yeah, you can show that. I guess you did that in the probability statistics class.
Yes.
Yeah. So sometimes we do things so important, but we don't realize why we are doing these things. But really, these are important issues. Variance, especially mean and variance for us, these two are way too important. Sigma square divided by, what is n? What is n?
Number of samples.
N is sample size, number of observations. Sample size. Sample size means number of observations in your sample. Okay, so you will see that later on. This is a very important y bar. You will see that y bar is one kind of estimator of mu. It's called maximum likelihood. When we do our econometrics, then we will do basically one method of estimation. 90% of the time we'll do one called ordinary least squares estimation method. And also I'll try to introduce another very powerful method of estimation. It's called maximum likelihood estimation method. You will see that basically we are trying to estimate the population parameters. So you know why everybody is kind of struggling, fighting. Everybody is trying to find the population parameter, which is not possible. So what they do, they use different methods to estimate the population parameter using those sample distribution. That is the whole point. So now, if you have a distribution y random variable with population mean mu, variance sigma square, then sampling mean y bar is also a random variable, and the mean of sampling mean is mu, variance of sample mean is sigma square over n, and being the sample size. Then if the population distribution, y here is the random variable, there is the population distribution, also called parent distribution. Parent, mother distribution, y is the original distribution. If y is normally distributed, then y bar is also what?
Normally distributed.
Normally distributed, no doubt about it. So this has to be clear now. If y, the parent distribution, is normal, and when they say normal, you know what it means. Normal means what?
Symmetric.
Normal means with that density function, ugly looking density function, very nice looking density curve, symmetric distribution, mean, median, modal value exactly at same place. It goes from minus infinity to
Plus infinity.
plus infinity, bell shape, skewness, curve, all the good properties of a distribution holds. If y is normally distributed, y bar, sampling mean, is also normally distributed, period. So no doubt. Let me summarize here once again. This is a so-called sampling distribution. If you have a random variable, you draw a random sample from that population. Then if you calculate the mean of that sample, which is sampling mean, that sampling mean is also a random variable. That means that has a distribution. If y is distributed with mean, mu, and variance sigma square, y bar will be distributed with mean, mu, and variance sigma square divided by sample size. Number 3, if y is normally distributed, y bar is also normally distributed. We need this normality, only too much. That's why we are kind of focusing on these kind of issues, normality. Now, so that is so far so good, okay? Here. Now, problem arises. Let's say we don't know whether y is normally distributed or not. If we don't know the distribution, nature of the distribution of parent variable, parent distribution is unknown. So simply it means if y, the distribution of y, whether it's normal or not, we don't know, then what will happen to y bar? Any guess? Hello.
Professor, can you repeat the question?
So far these 3 lines are okay.
Yes, Professor.
Y is random, y bar is random. Y distributed with mean mu, variance sigma square. Y bar is distributed with mean mu, variance sigma square over n. Y is normally distributed, y bar is also normally distributed. So far so good. Now I'm asking, if we don't know the distribution of y, let's say we don't know whether y is normal or not, maybe y is not normally distributed, then what happens to the distribution of y bar? I mean, what would be the nature of the distribution of y bar? Remember, nobody will get mu. We only have this y bar, poor y bar thing. That's what we only have. What will be the shape of the distribution of y bar? Okay, so last thing about statistics, probability statistics. There is something called central limit theorem, CLT, central limit theorem. Much used and abused theorem. Actually, more abused than used. Central limit theorem is saying if y bar, if the distribution of population is not known, if we don't know whether y is normally distributed or not, regardless of the distribution of y, the distribution of y bar, sample mean, gets more and more like normal, becomes more and more normal as sample size increases. Hopefully, if sample size is 30, regardless of the distribution of y bar will be distributed approximately normally. Sample size 30 is a big sample size in statistical standard. So if the distribution of y is not known, maybe not normal, y bar distribution of y bar will be getting closer and closer to normality as sample size gets bigger and bigger. And so if sample size is big enough, y bar will be normally distributed. Central limit theorem.
Professor, can you please explain again?
So maybe let me see if it's in the book. I'll show you. So what it's saying is, let's say we don't know whether y is normally distributed or not, okay? Regardless of the distribution of y bar will be normally distributed as sample size gets bigger and bigger, larger and larger. So with a big sample size, y bar will be normally distributed, even though y was not normally distributed. Let's see it in the book. But do you see what I mean here?
Yes, Professor.
Yes.
So if you draw a distribution of y bar where sample size is, let's say 30, the distribution will look like what? Like a normal distribution, symmetric, mean, median, mode, and value on the same place. It goes from minus infinity to plus infinity and so on. If sample size is large enough. What is that theorem? It's called central limit theorem, law of large numbers. And this central limit theorem will be used a lot. If you do something not normal, say, oh, okay, we have large sample size, so we can justify. Let me see if it's in the book, the central limit theorem. This is the layperson way of explaining, just to give you the intuition of. Yes, go ahead. Yeah, your question, you go ahead.
Professor, so in that case, the sampling will be more than 30. You are saying
30 is a number they're considered to be large. Yeah, it can. If the more the better. Okay, if you have a sample size of 200, that will be even better. Then y bar will be what? Surely y bar will be normally distributed. Yeah, the more the better. Always you think a sample size, larger sample size is always better. I mean, more or less. Yeah, because then you are gathering more information.
Professor, central limit theorem is on page number 890. I found it.
Page number
890.
Okay, let's see. Let's see if I can pull the book and see. It's a very interesting law of large numbers. Anybody read a book called Foundation? Fiction, science, social science fiction. Have you heard of the book that Foundation?
No.
Have you heard of this famous guy, Isaac Asimov? Foundation is a world by itself. So in that foundation, so it's a digression, okay? We are doing serious stuff. It's a digression. So there is a huge separate world in the galaxy. Let's say 10,000 years from today, human civilization is spread all over the galaxy and all this and that. There, at one point, one guy called Harry Seldon, he invented a new discipline. He called it psychohistory. So on the basis of that new discipline, you can predict the future. You can predict the future of a human society. How do you do that? With the help of large numbers. He said, what he says is almost like what we are doing in econometrics. He says, you cannot predict an individual. An individual has too much randomness. But if you talk about large number, mob, a lot of millions of people, then you can predict how they behave. So in econometrics also, basically what we'll do is we'll predict a lot of people's behavior on average, how they behave. What is the page number you said? Huh? Here is the thing? Hello? Somebody gave me the number.
If you search in the PDF, you need to write 893.
Huh?
If you are searching in the PDF, you need to write down 893. It will come automatically.
893.
Yeah. In the book, it's 890. But in the PDF, you need to write 893.
Okay. Here. You see, if the independent random variable, all of which have the same PDF with mean, mu, and variance sigma square, and then sample mean, summation x over n, sample mean, as n increases indefinitely, that means technically they are saying it to infinity, but infinity means in statistics, let's say more than 30. So what it's saying is x bar is distributed. What is this n standing for?
Professor, can you share your screen?
Okay, I share. New share. Can you see now? Hello?
Yes, Professor, we
What
can
I'm saying is, if these x's are the random variables, no assumption about the population distribution. They are not saying it's normal or not normal, so they don't know the distribution of the population. So then they are saying x bar, which is sample mean, will be normally distributed. You see, normally distributed as n gets infinity. Infinity is a technical saying, meaning large sample size. If sample size is large, then x bar will be normally distributed. Did they give any diagram? They did not give any diagram, I guess. Yeah, any statistics book will give you a diagram. So no, they did not give any diagram. So that's what it's saying, central limit theorem. Don't forget this central limit theorem. This is what will justify a lot of things in future. Okay. Sampling, distribution, mean, variance. Let me show you one thing, I guess. Yes. Oops. Let's share this. Okay, last thing. do you know how to find the expected value of y bar in all this? Huh? How to find the expected value using the expectation operator and variance, using the operator variance operator or expected value operator. Let me show you quickly here, I guess, before we move on. Here, let me see how we. So, expected value of y bar equals y1 plus y2 plus y3 plus divided by n. Isn't it the expected value of y bar? Is it this? Hello? Huh?
Yes, Professor.
So there's a lot of theories behind an independent distributed and also. So now think about it. What is the expected value of y1? If y is a random variable, this expected value of y1 is also mu. Expected value of y2 is also mu, and so on. So how many mu's will you get?
N. N.
N mu's divided by. So let me write. N is just sample size, a constant value. Copy. Mu plus mu plus mu plus mu divided by, which is giving you what? N. And mu over and
Is equal to mu.
you can show it with variance. Use the variance operator and you do it. I'll give you some practice, and there you will show it the sentence. So I guess that's all about the statistical review from my side. If you have any question, you can ask. No. If not, then yes.
I have confusion regarding the central limit theorem. Like
Yes.
the one in the textbook, like they have shown an equation, right? So like I'm not sure about
it's the same thing. What is
same
it?
thing which you showed right now.
Yeah.
So
What is
why
it?
did you write it under sampling distribution of sampling mean? That's what I was wondering.
What?
I have confusion regarding central limit theorem.
Yeah. What is your question?
My question is, what's the equation for central limit theorem? Like in the book, they have given an equation, right?
Equation.
Like
Yeah. What equation? What equation?
X bar tends to n
Yes.
mu sigma squared divided by n. So does that mean like X bar tends to the normal distribution of population mean and the population variance.
No.
That's
The central limit theorem is about the normality.
Okay.
You missed the underlying issue there. Okay. Let me open it again. To miss the main point here. If population distribution is normal, sampling mean distribution will be normal, and the mean and variance are what we said. They're right, but the distribution of the sampling mean, what will be the shape if the parent population distribution is not known? That is the whole point.
Bell shape.
Huh?
Same as the normal distribution shape.
If the shape of the the population distribution, whether it's normal or not, is not known, then what should be the distribution of the sampling mean? That is the whole point. And you will see that they are bringing normality there. Central limit theorem is telling you that the will be the sampling mean will be normally distributed if you have large enough sample size. That's the whole point.
Thank you.
Is that okay?
Yes.
Yeah, that's what they're telling. If you look at the lines they have written, you will see that when they were writing x1, x2, x3, they did not mention whether it's normal or anything else. Do you see that?
Yes.
Yeah, it has to be. Anyway, so let's go ahead. Yeah, no worries about that one. Now, let's kind of start our anything. Okay, before moving on to the actual econometrics, let's fix our quiz. I'm thinking of giving it on Sunday. So a week from today. It will be short, 30 minutes to 40 minutes. Sunday in the class.
Professor, can you repeat what you said?
Professor, can we give it on Tuesday?
See, it will be it's already late. Okay, you can do it on Tuesday. No, I don't have any objection, but our midterm cannot be shifted.
Okay, because Professor, we had HBS exam and other professors also gave quizzes, so we couldn't prepare well.
When are they giving quizzes?
On days like 22nd, 23rd, 26th, 30th.
Okay.
Submissions and quizzes. Sorry.
Yeah, 26 you give and 27 is another one. Do you have a quiz on the same day, 27?
But Professor, on Tuesday it would be better. We could prepare well.
Other people, what do you think?
Professor, no problem.
So are you talking about next week?
Yeah, just 1 week from today.
No, Professor.
Professor, is it possible to give on Tuesday instead of Sunday?
What I said is, I can shift the quiz on Tuesday, but midterm, not negotiable. Okay.
No problem, Professor.
What is the date for midterm?
Look at the syllabus. It's, I think, on the 4th or 6th October. Whatever, we cannot change that date. Okay. So quiz Tuesday is fine with me. If everybody else also is fine, or we will bring it on Sunday. So Tuesday.
Sir, what is our syllabus for quiz?
Whatever we cover, okay.
Professor, how will be the question format for the quiz?
Huh?
MCQs or like?
No MCQs. No MCQs. Conceptual questions, maybe a little bit of small problems.
Professor, can you give us some like questions so that we can practice? Like not exactly the question, but the
do you want me to give you the questions?
No, not like the whatever will come in the exam, but we want to like exercise some.
Okay.
Similar question, Professor. If you could give us for practice, it would be helpful.
Okay, let's see.
Yeah, what kind of question can be?
Okay, it will be mostly the review. Okay, so you already know everything there. So mostly statistical review and a little bit of econometric questions if we can. So,
Professor, what's the exact syllabus?
pardon me?
What is the exact syllabus?
Whatever we did in the class.
Professor, also for the midterm, like till we cover
Everything. Midterm is everything we did, we implied, we said, you asked.
Professor?
Yes.
Is the syllabus like whatever done in class till next Sunday or till this Sunday?
Sunday, Tuesday also. So
This Tuesday, Professor,
Sunday,
right? Not
Tuesday.
next Sunday.
Professor, this Tuesday, right?
Yeah.
I mean,
yeah. Yeah. Okay.
Professor, the quiz will be on this Tuesday or next week?
Not this Tuesday. This Tuesday is just day after tomorrow. I don't think you have time to prepare. It will be next week, coming week, Tuesday. Okay.
Professor, yes. And I have another question. Is it like, did you, it will be like MCQs or like short questions or
no
broad?
MCQs. No MCQs.
Okay, explanations, Professor.
There will be concepts, ideas, maybe a little bit of problems solving. Yeah.
Maths. Okay, okay.
Okay.
Yes, Professor. Professor, total marks 10 or 20?
Doesn't matter. It's a percentage is what
Okay,
matters.
yes.
If you want, I can give it
Yes,
to
yes,
1,000.
Professor.
You want 1,000?
Oh, no. No,
Doesn't
Professor.
matter. 10 or 10,000 doesn't matter. It's scale. Okay, let me show you some. It's a funny guy, or not funny. He's trying to explain it. I thought it would be good for you guys.
Professor, is it in the class time?
Yeah, it's a class time. Beginning of the class.
Professor, which chapters we have?
Hmm?
Which chapters we have?
Question? Other question?
Which chapters we have for the quiz?
Everything we did so far. Basically, we did some statistical reviews, okay? So, nothing much. I'm not sure if I can show this YouTube video to you, but I'll talk. I will not let the guy talk because he speaks.
Professor, are you there?
I'm here. I'm trying to pull a YouTube video. Can you see this video? Hello?
Not yet, Professor.
Here in our document, statistical review.
Professor, it's written like you are sharing. Yeah, we can see now, but we can't hear anything.
Yeah, I don't want you to hear because you don't understand what he's saying, okay?
Okay.
Maybe most of you will understand. He is speaking some Urdu or Hindi or something, but it's directly from the Gujarati, so I thought maybe it will be, I'll give you the basics of this thing. Econometrics is like is quantifying the relationship among the variables. Okay, so as I said in the beginning of the class a month ago, you know, economic theories. What are the economic theories? Economic theories are nothing but relationship among the variables. So what type of relationship you have encountered so far?
Statistical relationship.
Statistical
relationship, right?
No, theoretical. So when you say economic theory, let's talk about one economic theory. What is an economic theory? An example of an economic theory. Hello?
Yes, Professor.
Give me a theory, economic theory.
Demand.
Law of demand. Yes.
Yeah, law of demand.
Law of demand is an economic theory. It's a relationship among variables. Quantity demanded depends on what?
Price.
Depends on price.
Own price, income of the consumer, or the price of the complementary good, or price of the substitute good, and so on. But basically, there are relationships among the economic variables. So econometrics is coming later. First thing is the theory. Do you recall any other theories you have learned?
Yes.
Keynesian theory.
Utility theory.
Utility theories. Utility depends on what?
Consumption.
It demands the consumptions of goods and services. Good 1, good 2. Okay? Quantity of goods you consume. Then utility depends on this consumption of goods and services. And macro theories like consumption theories, like Keynesian consumption theory, Milton Friedman's permanent income hypothesis, or Andrew Modigliani's theories. There are a lot of theories. What other macro theories you have learned?
Marginal rate of substitution.
Marginal rate of substitution? Yeah.
Harrod-Domar model.
Pardon me?
Harrod-Domar model.
Harrod-Domar growth model.
Harrod-Domar.
Solo Swan growth model.
Yes.
Yes. Lot of theories you have learned. So theories are nothing but a relationship among the variables, economic variables. So in econometrics, what we do is we use the economic theory. Okay, let's say a consumption theory. It's saying if income increases, consumer expenditure also increases. Okay, John Maynard Keynes absolute income hypothesis. It says income increases, consumption increases, but not 1 for 1. If income increases by $1, consumption increases maybe by 80 cents or 85 cents, less than $1. Then second thing is mathematical economics. What is the mathematical economics doing there? Taking the theory and writing it in equation, in mathematical function. So if you have a theory that consumption depends on income, how do you write in mathematics?
Y equal to M1 plus X1 plus M2 X2.
Y, what is Y?
Income.
Y
Income.
Y
Y
depends.
equal to income
Y is what?
on
Y is what?
Y is income.
Y is income.
Equal to M1 X1 depends on goods 1 and plus M2 X2
What does
and
it?
depends on good 2.
What is income depends on good 1 and good 2? No, a consumption theory, let's say, a consumption theory is a consumption depends on income, okay? So consumer expenditure depends on, it's a macro theory. It's a John Maynard Keynes, a macroeconomist. It's a consumption depends on income. So basically what he's saying is consumption is a function of income. Consumption is a function of income. How do you write that? C consumption equals F of Y. Can you write like that? C equals F of Y?
Professor, we can't see. Are you writing?
Because I am not writing that here on that screen. But how do you write consumption depends on income in mathematically?
Y is equal to F of C, right?
Y equals F of C or C equals F of Y?
equal to F of
C depends on income. Consumption depends on income. C equals F of
Y.
Y. C equals F. So that's a mathematical function. So now the also the theory says Y increases, C increases. It's a direct relationship. Y increases, C increases. And how do you write that? Let me see.
Y is proportional to C.
Y equals, which one is dependent, which one is independent?
Income is
Income is independent, consumption is dependent.
Exactly. Consumption is a dependent variable, income is independent variable. So there's a mathematical function you are writing. You are saying C equals F of Y. That means C is a function of Y. That means Y is independent, C is dependent. Now, Keynes also said, if Y increases, C also increases. Then that's a direct relationship. That's a direct relationship. Then you are going from economic theory to mathematical function. You are using mathematical economics there. And a linear function, what will be the linear function? If you assume that the relationship is linear, a straight line, linear. How do you write that? Anybody, any guess?
Y is equal to mx plus C.
Again, you are saying Y equals. What is Y? What is C? Which one is dependent? Which one is independent?
equal to
C equals to
My.
C equals to My plus A.
Oh, plus
Plus
E. Yeah.
A. Okay, that makes sense. It's a linear equation. C equals My plus A. In this literature, they would write C equals A Y plus B. So what is A? A is the slope, B is the intercept. Now, that's how you can write an economic theory in a mathematical manner. Okay, so this is important. Any questions about this? There, you have an economic theory. Keynes did not write the equation, but we are writing the equation using Keynes theory. What the value of A, will it be positive or negative? The value of the slope? The slope is positive or negative?
Positive.
It will be positive. Y increases, C increases. Okay, let's see what this guy has to say. So mathematical economics, this is not important. Mathematical statistics, application of maths in mathematics in statistics. That's what we are going to do. So here, let's move ahead a little bit and see what he has to say. I'll share this thing with you, even though you cannot, maybe most of you will not. Okay, so here. So we have theory, we have mathematical economics, and we will be using mathematics in statistics. That's why we spend so much time on statistical review. Okay. Mathematics, we did not spend too much time on mathematics. However, I hope you all know basics of mathematics. Before moving further, are we thorough about straight line, linear equation? Hello?
Yes. Yes, Professor.
Do you have any confusion about linear equation?
No.
You have to figure out now. Do you know a little bit of calculus, very basic?
Yes.
Yes.
Okay. If not, you have to tell me. When we use a little bit of calculus, you have to tell me. I spend much time on statistical review because mostly it's statistics. Math obviously is basic math, but we will refresh your memories as we go. So, statement of the economic theory, like I said, absolute income theory, if income increases, consumption increases, but if income increases by $1, consumption increases by less than $1, and so on. Then specification of the mathematical model of the theory. Here we did C equals AY plus B. Let's see how this guy did. You see, Keynes stated that on average, consumer increase their consumption as their income increases, but not as much as the increase in their income. I'll show you the full right there. Full screen. Yeah. So statement of the economic theory, as I said, consumer increase their consumption as their income increases, but not as much as the increase in their income. What is MPC?
Marginal.
If your income increases by $1, by how much your consumption increases? Once again, if your income increases by $1, by how much your income increases is called the MPC. That is the, so when you specify the mathematical model, the one we did, Y, what is Y here? Don't get confused. Y is the consumption. Y is the, so this is by convention, okay? This is by convention, don't get confused. By convention in econometrics, Y is the dependent variable, X is the independent, is in any mathematical model. Y is the dependent, X is the independent. So in our model, what is Y? Y is the consumption. What is X? X is the income. Y is the consumption, X is the income. So is it a linear function? Beta 1 plus beta 2x. It's econometric convention they are using. What is beta 1? Is the vertical intercept. What is beta 2? Is the slope. Let me pause here if you have question you, because you might be confused here. So this relationship where Keynes is saying income increases, consumption increases, is written here in mathematical way. It's saying Y, which is consumption, equals beta 1 is a constant, plus is a plus here, beta 2x. Beta 2 is the slope of this straight line. Is it a straight line? Y equals beta 1 plus beta 2x?
Yes, it's a straight line.
Beta 1 is the intercept. Beta 2 is the what?
The slope.
Is the slope.
So
So
why the slope is the negative?
pardon me?
Why the slope is negative?
Active?
It should be positive.
Yeah, it's positive here. Yeah, it's positive. It's a typo here. Okay. Beta 1 plus beta 2x. They will write it later on. Beta 1 plus beta 2x. Okay. Any other questions? Hello? Hello? Are you guys with me here?
Yes,
Yes,
Professor.
Good. So, what is Y? Y is the consumption or consumption expenditure, dependent variable. What is X? X is the income, independent variable. Beta 1 is the intercept, basically vertical intercept. Beta 2 is the slope. Why is this thing here? 0 less than beta 2 less than 1. Beta 2 lies between 0 and 1. What is it telling you?
slope is lies between 0 to 1.
It
should be positive.
But less than
1.
less than 1. Give me a number less than 1.
It's half, maybe 0.5.
0.5, 0.6. Let's say 0.6. What is it telling you? Let's say beta 2 is 0.6. What is it telling you?
It should be a positive number.
Yeah, but obviously 0.6 is a positive number. But, yeah, how do you explain that in this context?
If X increases by 1 unit, then
What is the unit here?
Dollar.
Let's say dollar, okay.
okay, if X increases by $1, then Y will also increase by.
What is Y? What is Y?
Y is the
Consumption.
Consumption.
will
Increases by?
By 1.6.
No, by beta 2.
Yeah. What is beta 2 is 0.6.
$0.6.
Yeah, that means 60 cents. So that's just telling you if income increases by $1, your consumption increases by 60 cents. What is beta 1? How do you explain beta 1 here? Is the vertical intercept. In this literature, just say called intercept. How do you explain beta 1?
Vertical intercept.
Yeah, how do you explain that?
If the income is 0, so the consumption is beta 1.
Yeah, if income is 0, then consumption will be beta 1. This is called autonomous consumption. autonomous consumption. Beta 2 is the slope equals marginal propensity to consume. Okay, beta 2 is the slope, also called the marginal propensity to consume. Beta 1 is the intercept, also called the autonomous consumption. Why? Because when x is 0, y equals beta 1. So even if you don't have any income, still you consume little bit, and that is called the autonomous consumption. Question?
Professor,
Yes.
for beta 2 equals to 0.6, so doesn't it have to be like if income increases by 1 unit,
$1.
consumption $1 consumption decreases by
0.6 dollar. No, this negative is a typo. Here is a plus sign.
It's a plus?
It's a plus. This is a typo from their point, okay? This is a beta 1 plus beta 2x. Y equals beta 1 plus beta 2x.
But won't there be any possibilities that like it can be negative?
No. It's for a country. It cannot be negative. If your income increases, your consumption will increase for the nation.
According to Keynesian theory.
Yeah. Not only according to Keynesian theory, look at your macro national income accounting. Did you do national income accounting?
Yeah, we did
GDP?
Yes, yeah, we did.
Did you do with me principles at least? Or somebody
Principles
else?
of macro?
Huh? MA, macro.
Yeah. I did principles of micro with you.
Micro, no, I did not do principles of micro.
No, I did not do principles of macro with you. I did.
Okay. So if you do with me or with somebody else, you will see that consumption is the biggest header in the GDP measurement, GDP accounting. So your income is high, your consumption is also high.
Consumption equal to investment.
Yeah. So beta 2 is this restriction is reasonable. This restriction, beta 2 lies between 0 and 1. If your income increases, your consumption also increases. This is a plus sign here. It's a type. There's another typo I can see now. It's a beta 1. Slope coefficient is not beta 1. Slope is beta 2. So listen to what I'm telling you, okay? Y, consumption. X, your income. Beta 1 is the intercept. Beta 2 is the slope. The equation is y equals beta 1 plus beta 2x. How do you explain beta 1? If x is 0, consumption will be equal to beta 1, which is also called autonomous consumption. How do you explain beta 2? If income increases by $1, consumption increases by beta $2. Now, beta 2 is less than 1. So we took a number 0.6. This is just made up number. It's telling you this. If X, that means your income increases by $1, your consumption increases by 60 cents, $0.6. So on. All right. Question about this equation anymore? Hello?
No,
Yes,
Professor. Can we have 5-minute prayer break?
Prayer breaks. What time is it?
6:13 now.
6. Yeah, you go. Less 5 minutes will be okay. I cannot say no.
So we have 15 minutes for the class to end.
15 minutes only. So yeah. Can you offer a little bit later? Let's say 10 minutes later. Will that be okay, or you have to go now? It's a
Okay, Professor. Since the recording is there, so I'm coming back. It's
okay. Yeah, please quickly come back.
Okay. Thank you, Professor.
Okay, so these things are explained. So here they have drawn that line. what is this? What is the horizontal axis? Income. Vertical axis, consumption expenditure. Is income, consumption expenditure, and the straight line drawn. What is this distance? Intercept. Vertical intercept. This is the autonomous consumption. Even if your income is 0, you still consume this much. That is your beta. What is the slope? Slope is beta 2, which is MPC, marginal propensity to consume. It's telling you if your income increases by $1, your consumption increases by beta $2. All right, so this is fine. This diagram is fine. Hello?
Professor, can you just tell me a little bit about of beta 2 minus MPC?
Not minus, beta 2 equals MPC. What is beta 2? What is beta 2?
That
the slope.
Yes.
What does the slope mean? Slope means if income increases by $1, by how much your consumption increases. That is by definition the marginal propensity to consume, MPC. Slope is the MPC. Question? Hello? Slope here in this consumption theory context, slope is the MPC. By definition, slope means if your income increases by $1, by how much your consumption increases. That is also the definition of MPC, marginal propensity to consume. All right? Hello? Say something.
Yes, Professor.
Yes.
That is the that's what they are showing. It is not minus, it's equal. Beta 2 equals MPC. Then, from here, specification of the econometric model. How do you specify econometric model? What you did here is a mathematical model. Y equals beta 1 plus beta 2x. That's a mathematical model. Now, from mathematical model to econometric model, here you are using your so-called statistics. We'll give an example of from the book. Okay, we'll show the table, and we'll try to explain that a mathematical model is not enough to capture real life facts. And then we will talk about an econometric model. For now, you just know that the model, mathematical model we have shown is called an exact model. Exact model, one-to-one correspondence. Remember one-to-one correspondence? Hello?
Oh, Professor, can you please?
One-to-one correspondence. If I give you X value, you will get a Y value.
Okay.
Exact relationship. It's a mathematical function. It's an exact relationship. If you know beta 1 and beta 2, if I give you an X value, you will automatically get an Y value. Okay? Any X value, you will get another Y value. One-to-one, exact relationship. But you will see that in a later with the example, you will see that that exact relationship does not hold in reality. So we have to use something called an error term. u, an error term. So this was the model. Y equals beta 1 plus beta 2. It's a beta 2x. Beta 1 plus beta 2x plus a random term, an error term, also called a disturbance term, a stochastic term. This u, look at this u closely. This guy is the core of everything. This guy u is the core of everything. So why is it there? We will know gradually. But any econometric model, you have to add a u term. This u has many names. Why is so important? Different people call it differently. Some people call it a disturbance term. It's disturbing the exact relationship between y and x. Some other people are saying this is an error term because it's an error. It looks like an error from the exact relationship. You give me an x value, can I give you an exact y value? It looks like it's not possible. So you add something, you subtract something from y, you get a value. So also called a stochastic random term. Without that, there will be no econometric model. Today, I would like to emphasize that never give me any econometric model without a U term. If you give me an econometric model without a U term, 50% points will be deducted. What did I say? Hello? Hello?
Yes, Professor.
Yes, Professor.
If you write any econometric model in your research, in econometrics class, if you write an econometric model without a U term, you will be penalized heavily. There is no econometric model without a U term. You will see later on why U is the most important thing in econometrics. This is a random variable. Now, do you remember what a random variable is? Huh? What is a random variable? Hello? What is random variable? Nobody wants to speak? Hello? Let me ask.
Yes, Professor.
Okay. Afia, what is a random variable? Huh? Afia?
Professor, is that some value that like the value like there are some unknown values?
No, the whole probability statistics review we did, we started with random variable. Always we have been talking about random variables. Now you forgot what a random variable is?
Professor?
Yes.
Random variables are two types, discrete and continuous.
Yeah, but what is random variable?
You take random values and XY values and...
You forgot everything. You did not look at the lecture notes. You did not listen to the record. That's the problem with the recording. I know it's not your fault. It's human nature. You know, everything is in record, so I listen to the record before the exam night. This is human nature. This is not only.
Professor, I think random variable is a variable where the values depends on the outcome or result.
No, that's not what we said. We said a random variable is a variable where each value is assigned probability. Obviously, it's coming from is coming from the trials. It's coming from the experiments. Outcomes of the experiments can be used to generate random variables, but random variables are, the values of random variable are assigned what? Probabilities. So each value takes occurs with certain probability. Random variable, let me show you random variable. I have to switch to random variable. You will, so that where is that? Now that's the whole point of doing this thing. The whole econometric statistical review we did is give up. You look at the lecture notes where we did random variables and all this. So okay, we'll come back to our model. Random variable. You listen to the lecture notes or you look at your statistical appendix. So that's the whole point. That's where statistics is kind of playing the role in the randomness. In the randomness, in this U term, random variable. Anyways, the relationship is not exact. Relationship between X and Y, and we'll explain in later on why in the real life the relationship is not exact. Look at this. What are these values? So what is here? Y. What is there? X. Y and X. So look at these dot points. What are they?
Professor, these are the income.
So they're
X, see, X and Y. This is X and Y plane. So any point has got how many values? It's a Cartesian quadrant. It has got any point has got two values. One, the first one is what?
Consumption.
First one is income, second one is consumption. So look at this. Is the relationship exact? Here is income, this much income, consumption is this much. Income, here, how about this? This point?
Income. A little increase in income and increase in consumption.
Increase in income? How do you see increase in income here? How much is income here? This much. Consumption? Yeah. Consumption?
More.
Here, what happens? Income increases, consumption? Decreases.
Yeah.
What is here?
Income increases.
Income increases.
Consumption increases a little bit, but compared to this, consumption is?
Less.
Decreased. You see the way. How did you get these points?
X and Y value.
Professor, X value and Y value.
Yeah. So what is X? Income. What is Y?
Consumption.
Consumption. So from X and Y, how did you get this X and Y? You actually collected a sample, okay? You asked the people, okay, what is your income? What is your consumption? What is your income? What is your consumption? So one guy says, my income is, let's say 800. My consumption is how much? Huh? Give me a number.
900.
No, let's say 700. Another guy here, let's say here, says income, how much?
200.
Huh?
Income is.
Take these 2 points, okay? Here income is 800, consumption is 700, okay? Here
1000.
1000, consumption is?
Consumption should be 600.
600. Is that possible? Yes, that's possible. Some people are miser than others. Are you miser?
No, professor, in between.
In between, meaning
yeah.
Neither miser nor what?
Yeah, because I'm like, I don't waste money like for any silly thing. So if I need, then I spend.
Okay,
if I don't need, so why I should spend my money?
Okay, reasonable. But you know, people are different types. So some people with low income, even low income, spending almost everything. Some other people with high income, spending less
money.
So then you get all these points from asking people. And then where is the exact relation? Is there an exact relation? If you give a X value, you give Y value, X increases, Y increases, but it looks like not true. That is the inexact relationship. Inexact. Yeah.
Can we end here today because I have another class?
Oh, okay. We are done?
Yeah, the class is over already.
Class is over? Well, okay.
Yes, professor.
All right, then we call it a day today. We'll come back on Tuesday, okay?
Yes.
Okay, Professor, one thing.
Yes.
Did you finalize the like date and time for the quiz for Intermicro?
The quiz is Tuesday last time.
No, Intermicro.
Oh, Intermicro. No, Intermicro most probably Saturday. We'll have to do it on Saturday.
Professor, for this course, when will be your quiz?
Professor, it's 29 for this.
For
class.
this course, Tuesday.
Yeah, it's 29.
Okay, 29. But we cannot change the midterm, remember?
Yes.
All right, guys.
Okay, thank you, Professor.
See you on Tuesday.
Okay, Professor, and share the recordings with the TA so that we can get it. Because last class record we didn't get.
Okay. All right, I'll share. Is it YouTube? You can find it on YouTube, but you cannot.
But Professor, we also need the class recording.
Yeah. For the last class.
We didn't receive last class recording.
I'm gonna share. Okay. No worries.
Thank you, Professor.
Yeah. All right. Bye. Bye.
Bye, Professor.
Bye.
Bye, Professor.